Hi everybody, welcome to another video in Calculus 2. We go to section 12.2, polar coordinates. Of course, we studied this before in pre-calculus. So this is more or less, it's just a review. We don't even have any calculus in this section, so this will not be very long section. Alright, polar coordinates. So polar coordinate, the way we define originally in the what we call xy coordinate or the rectangular coordinate or Cartesian coordinate, we have a point x and y given by the x and y coordinate. Now, instead of doing that, we define a point on two-dimensional plane as follows. First, we will have a point. So there will be the origin is called a point, and then there is an axis. This is the axis, so it's only go one side. That side, and that is the polar axis. And then from there, we have array, and we rotate that about from the polar axis. So first, whatever the point we have, we will have the distance r that is called the radial coordinate. So the distance from the point to whatever the point is, we call that r. And then the angle make from the polar ray to wherever the ray that contain the distance of the point to the point, we call that the angular coordinates, theta. So the point x and y that will be given as the r and theta. So instead of represent the point using x and y, we represent the point using r and theta. Right. So from that point, we can write as r and theta. So r and theta is called polar coordinates. Right. Now, more on that. Now, on trigonometry, when we define an angle, usually positive, actually it's not usually, positive is going to be counterclockwise, and we can go extra revolution if we want to. So we can go that and then just keep going. And every time we go an extra revolution, that's 2 pi, we still have the same what we call the coterminal angle. So if we have the same terminal rate, we have coterminal angles, and to get to coterminal angles, we'll add 2 pi to it. So we can go around and around and around. As long as we stop on the same ray, the point will be the same. So normally we have the point r and theta. It could be r theta plus 2 pi, or in general we can just say this point, the point r and theta will be represent the same as r and theta plus 2n pi, or 2 pi times n, where n is any integers. So this set of points represent the same point as r and theta, because we go around and have the same terminal ray. Right. So that is one way to do that, is to go to coterminal angles. Now, a different way to do that is, now instead of go this angle theta and then the distance r, what we can do is we can go this angle theta plus pi. So if we add a pi to it, we go an extra half revolution, and we have this ray. Now, if we talk about positive R, we will go in the same direction as wherever the angle stops, so it will be in this direction. But if we use the opposite R, we will go opposite direction and go back to that point. So one way to represent the same point using that, or we can use the opposite to R and an angle. We can add pi to it. And then again, we also have coterminal angles, so I still have 2n pi. So all the angle in this representation will be the same. All the points in this representation will be the same as this representation and the same as that. Right. And usually we define R to be positive. Regardless, this should not even matter. Opposite R will be go to opposite direction. Right, now graph the following points in the polar coordinates and give two alternative representation for each point. Alright, first the point is 1 and 5 pi over 4. So 5 pi over 4, that is 5 quarters of a pi. So 1 pi is 1 revolution, and then a fourth, and then an extra quarter, so it's going to be this point. Yeah, so you will see it. I wrote a concentric circle, and that is the circle of radius 1, so we have that point, Q. Now, so that is the point. If we want two more representation, we can just add 2 pi into it, and we can say, how about 1 and 5 pi over 4. How about we add 2 pi to it? We get the same point. And 2 plus 5 over 4 is 13 over 4, but okay, 5 fourths plus 2 change the fraction, 13 over 4. So we might have the representation of 1 13 pi over 4, which means we go extra revolution there. Or we can also have different representation using opposite to the radius, use negative to that, and in that case I will add half of a revolution. So we'll have negative 1 and 5 pi over 4 plus pi be 9 pi over 4. So these two representation represent the same points as that. So if you add 2 pi, get back to the same thing. Add a pi, go to opposite direction, and then we turn the R to opposite, and that will be the case. Next, negative 1 and 7 pi over 4. So, by the way, if it is 1 too small, make it 4. Right, negative 4 and 7 pi over 4. So 4 is here. So this is the circle of radius 4. Uh, 7 pi over 4 will be over here. However, this we have the negative. So instead of going 7 pi over 4, negative 4, meaning we have to go the opposite direction as where we stop. So we stop here, we have to go opposite direction. So actually it will be this point is the point R. Right, if we need two more representation, one way to do that, of course, we add 2 pi to it. Or if we don't want to add 2 pi, how about we subtract 2 pi? Still the same thing. We can just subtract 2 pi. That certainly works. Add 2 pi or subtract 2 pi, still the same thing. 7 over 4 minus 2 will be negative 1/4. So we have negative 4 and negative pi over 4. So that is one representation of the same point. Now, if we don't want that, we can just negate, turn the raised to opposite. So instead of negative 4, it's going to be 4. But when we do that, we have to go an opposite point from it. So to get to opposite, either we add a pi or we minus a pi to it. Still the same thing. Yeah, we can add or we subtract a pi here. It's still the same. I use subtract here. So that gives us 4 and 3 pi over 4. So in that case, we just go 3 pi over 4. And then just go 4. And that will be the same representation. Right. Next, 2 and negative 3 over 2. So this is the circle radius 2. And we go to negative 3 pi over 2. 3 pi over 2 is like 270 degrees. 3 pi over 2 is there. But it is negative, so it goes clockwise. And we will stop here. So this is point S. Right, so if we want the same, the different representation for the same point, we can just add 2 pi or subtract 2 pi to it. In that case, we have 2 and pi over 2. Or we turn the distance to negative, and we add a pi to it. So add a pi, change the sign up, or add 2 pi, we don't change the sign. So, or we add the pi, we change the sign, add the pi again, we change the sign again. So that's why multiple of 2 pi, the sign will stay the same. Multiple of, and I should not say that, just add a pi, an odd number of pi, we will change the sign. So we see we can just go half, that's negative pi over 2, and then go the opposite direction to that. We have the same point S. I said none of this should be new, because we learned about that in the trigonometry and with calculus. Right, next. Converting between rectangular and polar coordinate. Definitely we have to know this. Right, so if we have the point X and Y, and also if we written in the polar coordinate R and theta, so in this case we have R and theta, and then we have X as this distance to the y-axis, and Y is the distance to the x-axis from the point. So obviously we have the definition of the trig function. Cosine of theta is cosine of theta adjacent over hypotenuse x over r. So in that case, x multiply r on both sides is r cosine theta. And then we have sine of theta is opposite over hypotenuse. So y is r sine theta. Right, which is what we have here. And then Pythagorean theorem, we have r squared equal x squared plus y squared. And then finally, tangent of theta opposite over adjacent. So we have that. Just one thing though. There's the asterisk here. So whenever we do this, remember, tangent of theta is y over x. So y over x, both of them could be negative. In that case, that's the same as y over x. So the asterisk there is, whenever we're using this one to find theta, make sure we have to check the quadrant. When solving for theta using that formula. Other than that, it should be simple. Right. Let me write that out again because that is important. X equal r cosine theta, y equal to r sine theta. X squared plus y squared equal to r squared. And tangent of theta is y over x. And I'm going to put the asterisk there. So be mindful with that. Right. Express the point with polar coordinate in Cartesian coordinates. By the way, Cartesian is, did we say that? Oh, it's another name for rectangular coordinates. Right. So we have what we are given is this point in polar coordinates. So from here we say r is equal to 2 and theta is 3 pi over 4. So we have r and theta like that. It's easy. X equal to r cosine theta. 2 cosine of 3 pi over 4. Cosine 3 pi over 4. Negative square of 2 over 2. So negative square root of 2. And then y is r sine theta. 2 sine 3 pi over 4. Sine 3 pi over 4 is positive. Square of 2 over 2. 2 and 2 cancel out, square root of 2. Right, so the point we have is x is negative square root of 2 and y is square root of 2. Just to make sure, we'll check the point. Right. Right, first, the point 2 and 3 pi over 4. 3 pi over 4 is 135 degrees. So it will be about here. Two and 3 pi over 4. Right, so the distance is 2, angle 3 pi over 4. Right, now if we write this into the x and y coordinates, x will be negative square root of 2, and y will be square root of 2. And if we want to, we can confirm that in a triangle, square root of 2 square plus square root of 2 square is going to be 2 square, which is, so that's correct. Right. So from polar coordinate r and theta, we go to rectangular coordinate, meaning x and y, and we found that to be negative square root of 2 and square root of 2. That's simple enough. Next, spread the point in polar coordinates. So we want the point in polar coordinate, meaning that we want r and theta. What we are given here will be in rectangular coordinates. So we have x equal to 1 and y equal to negative 1. And we will write this in polar coordinates. So we will find r and theta. So x squared plus y squared equal r squared, or r squared equal x squared plus y squared. Let's choose x to be positive. So we can do that. And we have square root of x squared. Sorry, x is 1. Y is negative 1 square. That's square root of 2. Next, tangent of theta is y over x. So tangent of theta is y over x. So theta equal tangent inverse of negative 1. Right. Usually when we use the inverse trig function, I will keep in degree mode. It is easier to know what is the angle. So tangent inverse of negative 1 is negative 45 degrees, or we can say negative pi over 4. Right. So just have that. Now, remember the asterisk. Every time we use that formula, just make sure that we check the quadrant. So, to check the quadrant, we don't have to do much. Right, 1 and negative 1, x equal to 1. Y equal to negative 1. So we're talking about this point. Yeah, about here. 1 and negative 1. Right. So if we want to turn this into r and theta, so the distance so if this is 1 and this is also 1, so those we have square root of 2 as the hypotenuse, which is correct, so that's good. And the angle is negative pi over 4. So yes, so that the answer works. So square root of 2 for r, and theta is negative pi over 4. If we want to be clear, even better, we say r theta equal to those. Right. Simple enough. Next, express this point in polar coordinate. So we already have this in rectangular coordinate. So we're going to write this in r and theta. Knowing that x is negative 1, y is negative square root of 3. Right, first, same thing. X squared plus y squared is r squared. So r equal to square root of x squared plus y squared. X negative 1 square, negative square 3 square. 1, 3 is 4 square, 4 is 2. And then the tangent of theta, y over x. Y over x negative square of 3 over negative 1, which is just square root of 3. So theta equal to tangent inverse. And tangent inverse of square root of 3 square root of 3, 60 degree, pi over 3. Right. So we always need to check the quadrant. Right. We have the point x equal to negative 1. Y equal to negative square root of 3. So we're talking about this point here, which the distance actually is 2. So the distance, the r is correct. So we don't need to check r. We just need to check the quadrant. R equal to 2, which is good. Now, the angle is pi over 3. If we go to the angle pi over 3, it will be 60 degrees. That is pi over 3. And of course, this is in quadrant 1, which is not. The point here is in quadrant 3. So make sure that it has to be in the right quadrant. So this is not in the right quadrant. So what do we do? Right. So when we have tangent equal to something, when we take the tangent inverse, remember the period of tangent is a pi. So potentially we can have pi over 3 plus a multiple of pi if we need to. And so in that case we choose some value for pi, some value for k, so that this will be in this quadrant. But usually if it is not in the right quadrant, we're just going to add a pi to it. So we have to add a pi to it. Then we start with pi over 3. And we add a pi to it. So it will be in the right quadrant. So we need to do that. So 4 pi over 3. 4 pi over 3 is in the third quadrant, so it's correct. So every time we use this formula, make sure we draw it out and make sure that it's in the right quadrant. If it's not in the right quadrant, add a pi to it to bring it into the right quadrant. So I just say need to be in correct quadrant. So sometimes we have to add a pi to it or subtract a pi to it. It's still just fine. Bottom line is the answer is r in theta is equal to we have 2 for r and 4 pi over 3 for theta. Right. Now I just remember one thing I forgot. It's not forgot. I did it correctly, but on page 123 and on section 12.2, when we try to find a point here and we find a values to check it. Bottom line is when we have cosine equal to 0, it could be pi over 2 or could be 3 pi over 2. So my point here is whatever we solve a trig function, it would be more than one answer. Let's choose the one that is good. So there's a lot of, so tangent equal to square root of 3, a lot of angle theta that have the tangent equal to square root of 3. We have to choose the one in the right quadrant. Just like in that problem, we have more than one values when we have cosine equal to 0. It just happened to check on the first one, so we don't have to go any further. But if it doesn't work, remember the trig function, trigonometric equation, there might be more than one answer. Right. Actually, we will do a lot more of that in the next section. But now we go continue reviewing polar coordinates and polar curves. So polar curves is pretty much the set of all the points given in polar coordinates. So now we have r equal to 3. Now r equal to 3, what is that represent? R equal to 3 meaning that we have all the point distant 3 away from the pole. So in that case we have the circle of radius 3. So that gives us a circle. Next, what is the equation? What is the curve or the set of points described by this? So pi theta equal to pi over 3. Pi over 3 is like 60 degrees. It is 60 degrees. So everything that line on this line. So if we have positive r with that direction, negative r this direction, but we're going to have the whole line. So this is a line, and the angle is pi over 3. We have positive r and negative r, so just a line. How about r equal to 2 secant? Now this is a little more work. R equal to 2 secant. So first secant is 1 over cosine theta. Multiply cosine on both sides. We have r times cosine theta equal to 2. And r times cosine is x equal to 2. So x equal to 2, it is the vertical line. If we want to graph in the calculator, we can do that too. Hit mode, function, parametric, polar sequence. We're going to graph the polar. If we're going to graph, make sure in the radian mode. Right. Let's graph. R equal to 2. We cannot type secant, but we can type one over cosine theta, and then we have the vertical line. Just make sure that we choose enough values so theta will go from 0 to 2 pi. Well, that's good. So yeah, that's the vertical line. And finally, what is r equal to theta? Now theta will be greater than or equal to 0. So as the angle increase, the radius increase. So we will start from here, and when the theta increase, the radius increase. So look like that would be spiral. Actually, it would be better if I just graph using the calculator. And then just keep spiraling out. If we want to go more than 2 pi, just hit Windows and go to, let's say, 5 pi. And here we let pi divide by 100. So every pi, it will graph 100 points. So it will go extremely slow, but we still have this spiral. And it is outside, we don't see that anymore. Just keep spiraling out. So it's not that bad. You just write the spiral. Right. So now, so what we have earlier is the equation of polar coordinates, and then we'll try to do that. Actually, more of that. Now, if we have the equation r equal to 6 sine theta, now we convert this equation into Cartesian product. So what is this equation look like? Remember, we still only have this. Only have that. So we have sine here. If we square both sides, we have r squared, which is great. R squared, x squared plus y squared. However, the sine theta is not very good. So instead of square both sides, what we do, we multiply by r on both sides. And I put the sign, the r right here. And r sine is going to be y. So we have r squared equal to 6y. And r squared is x squared plus y squared. So that's good. But what equation is this? Right now we don't see that very clear, but if I move the 6y to the other side, and I will do the completion square, just add something to this side, and we can add something on the other side. Things will balance. To make a perfect square, we take half of the middle number. So I take half of that, which is -3, and then I square it, be 9. So that complete square, and furthermore the complete square is going to be y and -3 square. And so this is the circle. And radius is equal to 3, and the center will be 0 and 3. Right, we can of course can graph it. 6 sine theta. So that is the circle. Because in the calculator, the width is longer than the height. So in that case, if we want to make it, the reason it's still running because we let it go from 0 to 5 pi. So if we just want one revolution, 0 to 2 pi. There, right. Now, if we want to have, actually I think there's more than one time around. How about just pi? Right. So as you see, it will take only a pi to go around that circle one time. Right. Because sine of theta equal to 0 when we have 0 and pi. So we start from r equal to 0, we go around, and get back to r equal to 0. So that's why we only need to go from 0 to pi to graph the whole curve. Right, now zoom number 5, we have the same increment on the x and the y axis, so that look more like a circle to us, so just good. Radius is 3, center 0 and 3, so yeah, that look right. Now earlier we convert polar equation r and theta into rectangular equation x and y. Now we do it in reverse. We are given x and y, can we turn that into polar equation? Once again, just these formulas. I'm going to write that out one more time. It doesn't hurt to do that. X squared plus y squared equal to r squared tangent y over x. I still put asterisk there. Right, y equal to x squared. Y is r sine theta, so substitute directly. And x r cosine theta. Of course, we have the square on this side, not on that side. Right, so y and then x squared. Right, and then we square that, we have r sine theta equal to r squared cosine squared. Of course, we can stop here, but we can divide by r on both sides. So sine theta equal to r squared divided by r on both sides. Then we just have r cosine squared theta. If we want to solve for r, we can write this as sine over cosine squared. If we want to, we can write divide by cosine squared secant squared, but that's not the point. So we can write equation in polar coordinate, just r and theta. Customary, if we can just solve for r, because we can put in the calculator if we have r equal to something. Right, actually let's just try that. Sine theta, actually fraction sine theta, and then cosine square yeah, so it is a parabola y equal to x squared. That works. However, it is not going to go like the parabola. It could go anywhere, but the combination of it will just have that. And once again, it's only from 0 to pi to have all of that. Yeah, sometimes we have to change the domain for theta to have the whole graph, but it's good enough for that one. Anyway, I said those formulas should be good enough. Same thing, y equal to 3x plus y plus 1. Y is r sine theta. X is r cosine theta plus 1. So of course we can stop there, but if we want to, we can always solve for r. So subtract r on this on both sides. Cosine theta equal to 1. Factor out r. And solve for r. Right, just graph that and see if we actually have it 1 over sine theta, oops, sorry, minus 3 cosine theta. Right, so that is the line 3x plus 1. So let's zoom in. It does go to 1 because the y-intercept is 1 and the slope look like 3. So that works. Right, I chose for R, so in that case I can graph it, but we don't need to. Any of this is good as the answer. Next, x squared plus y squared equal to 5. Well, this one obvious. X squared plus y squared is r squared, right? So in this case, r squared equal to 5. Check the square root on both sides. R equals square root of 5 or negative 5. I mean, plus or minus square root of 5. But usually we refer r to be positive, square root of 5. So we choose r to be square root of 5. By the way, it's not no big deal, but if you see the graph here, square root of 5. Yeah, so that's just a circle. Remember, we only let it go from 0 to pi. So if we want a whole circle, yeah, that's the whole circle there. Right. How about if we let it equal to negative? We still have a circle, but it's just starting from different point. So whether it's positive or negative square root of 3, square root of 5 is still correct. Right. Next we have symmetry in polar equation. By the way, you should see this in pre-calculus and trigonometry already, so we just go over quickly. So if we have replaced theta by negative theta and we have the same equation. So in this case, if we have a point where we go theta or negative theta, those points will be symmetric on the polar axis. Or if we want to do symmetric on the line theta equal pi over 2 on the y-axis, we're going to use theta, replace theta by pi minus theta, and we have the same thing. And if we want symmetric with respect to the pole, we just do this. I said just a review. For example, if we're talking about r equal to 3 cosine theta, so which is that circle, right? And this is symmetric with respect to the x-axis. So if we do that with negative theta, we have the same thing, right? Now, if you want to convince that it is actually the same thing, we can do this. Go back here, and when it highlights this, hit enter 1, 2 times. When it's flashing this, so it will graph a dot around it. So we'll see. First, it graph the circle, right? Actually, it go 2 times. Now we graph the second one. See, the second graph will trace on the top of the first graph, and it will go over the circle twice. Right, so we replace theta by negative theta, we get the same thing. The same equation. By the way, this is not one-to-one. It might start different point, but it will graph the same thing. Right. How about this? 2, 1 minus sine theta. Now if we replace and we replace sine pi minus theta, we should have the same graph. 1, 2, right? So the first graph is that. I need to zoom out, and you see the second graph. Will be traced around that. By the way, that is the graph of what we call a cardioid, or the heart shape. Right, so again, if we replace theta by negative theta and we have the same equation, the same graph, then yes. By the way, we can see this one is symmetric on the line on the y-axis easily. So pretty much if we can graph it, we can see the symmetry as well. So it's not a big deal. So if we have cosine, then cosine is an even function. So cosine of negative is the same as positive. So that's why it is symmetric with respect to the polar axis. Right. So that is the symmetry. Of course, we can confirm that by the graph easily. Right, now, graph this. I'm not going to just ask you to graph this because that's too easy, right? Actually, we're going to graph a bunch of them. Right, let me zoom in and see if I can actually get, yeah, much better. So what we see here is what we call is the rose petals. There are 4 petals, right? So when we have this, 4 petals. How about if we go to 3? Be 3 petals. How about 4? So how many do we have there? Right, each quadrant have 2, right? So 1, 2, 3, 4, 5. So it's 8. How about 5? So how many we have there? 5. So if we have an odd number, it will be the same as the number of petals. If we have an even number, it will be double that. By the way, notice if it is sine, it's that. Now if we switch to cosine, so first the cosine will just shift like 90 degrees. Let's turn that off. Now we have the graph of cosine. So cosine will go through the x-axis here. And now we have the sine. It will go through the y-axis. So we just rotate 90 degrees. Right. So let's just see the pattern that we have here. Right. Right. So I said the graph itself is not that big of a deal. Just see the pattern here. Right. Next we have y equal to 3 plus 2 sine theta and we zoom out. So this will be a carioid. Not a carioid, sorry. I don't even know the name for it, but of course I can check that. But let's change the windows. Let's go from negative 5 to 5 on the x, and negative 4 to 4 on the y. Negative 6 for x, 6 for x, and 6 for y too. Alright, how about that? Actually, it might be 2 pi, so make it 7. It should be more than 2 pi. Alright, that should be good. Alright, so what we have today. So this is not a carioid. Carioid have to have actually that's that point. If we want the carioid, we can just change this to 2, and now we will have a carioid. Should be a carioid. See, there is a sharp turn right there. Now, so we start with 3. It kind of curve. When we have 2, we have a point. How about we just go to 1? What do we have here? Right. So actually what we have is with a loop. Let me just zoom box. Right, we will zoom out that windows. So just like when we use a mouse. So we're going to zoom this windows. Maybe in the future we just use like touch screen and we use 2 fingers to zoom out. Forgot to hit enter. Okay. Do that again. Right, upper left corner, and lower right corner. Right, so that's what we have with inner loop. Right, so when we have, it's all about the ratio of those two. If they're the same ratio, it's a carioid. If the number constant is bigger, it kind of outside, and if it's less, there will be a loop. So we just have to work with a bunch of those numbers. And then the last one, I don't remember what it is, but it look interesting. If sine theta minus 2 cosine of 4 theta. And let's go to the standard windows. Right, so what we have, kind of like butterfly, upside down butterfly. Yeah, like I said, we can look at the graph. By the way, when we look at this one is symmetric on the line y equal to x, on the line theta equal to pi over 2. It's easy to see. And then just see the pattern about the rose petal and about the family of that function. Anyway, so we can graph and then we can see characteristic of those graphs. Anyway, so like I said, there's no calculus in this section yet, but the next section will study a lot more calculus related to the polar coordinates, but that one we do in this section. Thank you for watching.